TSI-Stroke multiplication structure, a VPT study of glucose, pulse pressure, and SBP, number 1645, May 16, 2026, Gerald C. EclaireMD Foundation. Category, VPT Stroke. Special note, this research journal is based on my personal research using data from my own body and is provided for educational purposes only. It does not constitute medical advice and should not be interpreted as guidance from medical professionals. Abstract, in this paper, I applied both Viscoelastic Topology VPT analysis and Viscoplastic Medicine Theory VMT energy analysis to study the internal structure of the TSI-Stroke equation. The TSI-Stroke model is based on multiplicative interaction among three major physiological variables: glucose, pulse pressure PP, and systolic blood pressure SBP. The purpose of this study was not simply to measure statistical correlation, but to investigate the deeper difference between geometric synchronization behavior and accumulated physiological energy behavior inside a nonlinear biomedical system. The statistical correlation analysis showed glucose versus TSI-Stroke, 60% PP versus TSI-Stroke, 50% SBP versus TSI-Stroke, 11%. However, the VMT energy analysis revealed a very different result. The total energy contributions from glucose, PP, and SBP were all close to approximately 1/3 each, indicating that all three variables contribute nearly equally to the overall stroke-triggering energy system. This finding suggests that statistical correlation primarily reflects time-domain geometric similarity or trajectory synchronization, while VMT energy analysis reflects accumulated physiological stress and nonlinear triggering force. From my viewpoint, glucose behaves primarily as a long-term structural stressor that slowly damages vascular systems over many years. SBP behaves more like a short-term mechanical hammer capable of producing acute triggering force. Pulse pressure reflects vascular stiffness and elasticity deterioration accumulated over time. The multiplicative interaction among these three variables creates a highly sensitive nonlinear system capable of rapid trajectory amplification. This study demonstrates why multiplication may better represent the dynamic behavior of coupled biomedical systems than traditional additive or purely statistical approaches. Preface: after surviving my hemorrhagic stroke on June 21, 2025, I became extremely sensitive to the dynamic interaction among glucose, blood pressure, pulse pressure, sleep, and vascular behavior. Over time, the TSI-Stroke model gradually evolved from a mathematical equation into a real-time sensing and feedback control system inside my brain. At present, I use this model continuously throughout the day. Every time my glucose rises slightly above normal, I immediately pay closer attention to both SBP and PP. I often perform breathing exercises to suppress SBP in order to maintain my TSI-Stroke value below approximately 95, a safer zone for me personally. Through repetitive daily observation, I gradually realized that glucose and blood pressure behave very differently in the time domain. Glucose behaves relatively slowly around each 10 to 15 minutes and smoothly, acting more like a long-term background structural stressor. Blood pressure, especially SBP, behaves much more dynamically, fluctuating rapidly around each minute with high-frequency oscillations and sudden short-term spikes. These spikes may only last 1 or 2 minutes, but they can generate extremely large instantaneous mechanical stress on weakened vascular structures. This difference eventually led me to recognize an important limitation of traditional statistical correlation analysis. Statistical correlation mainly measures geometric synchronization or curve similarity between variables over time. However, human disease progression is fundamentally an energy-driven process rather than merely a geometric process over time. For this reason, I decided to analyze the TSI-Stroke system using both Viscoplastic Topology analysis VPT for trajectory geometry behavior, Viscoelastic energy analysis VMT for accumulated stress behavior. The combination of these two approaches gradually revealed a much deeper internal structure hidden inside the TSI-Stroke multiplicative equation. Introduction: traditional medical research usually uses statistical correlation to determine whether a variable is important. However, from my viewpoint as both a math physics-based engineer and biomedical researcher, correlation alone cannot fully explain nonlinear pathophysiological systems. Correlation mainly describes whether two curves move together over time. In other words, it describes geometric curve similarity inside the time domain. But biomedical damage is not merely geometry. Biomedical damage is the result of accumulated energy. For example, an earthquake's shock wave may last only a few seconds, but its destructive energy can be enormous. Similarly, a sudden SBP spike may show weak statistical synchronization with glucose over long periods of time, yet still generate powerful vascular triggering force capable of causing a hemorrhagic stroke near the pontine location of my brain. This concept eventually motivated me to separate geometric synchronization behavior through statistics and accumulation behavior through energizing to different analytical frameworks. VPT and VMT. Research methodology of TSI-Stroke equation used in this study is based on multiplicative interaction among glucose, pulse pressure, and systolic blood pressure. TSI-Stroke risk equals glucose 120 * SBP dBP 45 SBP 120 *. Amplifier. The purpose of multiplication is to represent an amplified interaction behavior among three physiological variables. In arithmetics, addition assumes independence among variables, but multiplication assumes interaction and amplification. In real biomedical systems, glucose, vascular stiffness, and blood pressure do not behave independently. They continuously interact and amplify each other dynamically inside human bodies. The datasets used in this study were obtained from my own long-term longitudinal measurements, including high-frequency glucose monitoring 96 times daily, repeated SBP measurements 24 times daily, P calculations from SBP minus dBP 24 times daily. The study then used two different analytical approaches: statistical correlation analysis. This measures geometric synchronization between each variable and TSI-Stroke trajectories. VMT energy analysis. This measures accumulated viscoplastic energy contribution from each of these three variables across time. Research results. Statistical correlation analysis demonstrated glucose versus TSI-Stroke, 60% SBP dBP versus TSI-Stroke, 50% SBP versus TSI-Stroke, 11% from a traditional interpretation. One might conclude that glucose dominates the TSI-Stroke system while SBP plays only a minor role. However, the VMT energy analysis revealed a very different structure. The total VMT energy contribution ratios from all three variables was approximately balanced: glucose, approximately 33% PP, approximately 33% SBP, approximately 33%. These two different findings are extremely important. It suggested that statistical correlation and physiological energy represent fundamentally different properties of biomedical systems. Results discussion. This study gradually helped me understand the difference between geometry and energy. Geometry mainly describes trajectory, shape, and curve synchronization behavior. It is largely geometric. Nothing else. VMT energy analysis describes accumulated strain-stress interactions, damage potential, and triggering force. It is largely physical energy. These two systems may occasionally behave similarly, but they are fundamentally different. For example, glucose behaves like a slow-moving structural stressor. It continuously damages vascular walls over many years through chronic metabolic stress. SBP behaves differently. It acts more like a short-term mechanical hammer. Even brief high-pressure spikes can produce extremely large instantaneous mechanical force. Pulse pressure reflects vascular stiffness and elasticity deterioration accumulated over long periods of vascular aging. In reality, the geometric trajectories of glucose and pulse pressure are more similar to each other. Therefore, these three variables behave differently geometrically, but their total energy contributions can still become nearly equal. This is precisely why the multiplicative operation becomes critically important, because multiplication captures interaction with an amplifying effect. If glucose is elevated while PP and SBP remain normal, the overall TSI-Stroke value may still remain relatively stable. However, if all three variables rise simultaneously, even moderately, the multiplicative interaction co-rapidly amplify total stroke triggering energy of a stroke event. This nonlinear amplification behavior resembles many engineering systems where coupled variables create instability much faster than independent linear systems, from my viewpoint. This also explains why I suddenly experienced a stroke on June 21, 2025 despite only moderate abnormalities in individual biomarkers. The triggering mechanism may not come from one isolated variable alone, but rather from the multiplicative enteric among several partially abnormal variables occurring simultaneously over a considerable period of time. In my stroke case, my TSI-Stroke energy remained above 100 for about 1 year. From July 2024 through June 2025, I then suffered a hemorrhagic stroke on June 21, 2025. Further physiological interpretation or important observation from this study involves time domain behavior differences. Glucose usually changes relatively slowly over 15 minutes to 1 hour. Therefore, glucose trajectories appear smoother and show stronger long-term statistical synchronization with TSI-Stroke. SBP behaves very differently. Blood pressure fluctuates rapidly minute to minute due to emotional stress, breathing posture, emotion, autonomic nervous system activity, sleep quality, and vascular elasticity. Because SBP contains much higher frequency oscillations, its curve often does not match the slower glucose trajectory geometrically. Therefore, statistical correlation coefficient appears low. However, weak correlation does not mean weak physiological importance. In fact, sudden SBP spikes may represent the immediate triggering force responsible for vascular rupture. This distinction between geometry and energy became one of the central realizations of this study, which involves both mathematics and physics. Interpretation of the post-stroke January to February 2026 pivot observation. TSI-Stroke value decreased from 98.3 in January 2026 to 93.6 in February 2026, indicating overall improvement. However, during the same period, the cumulative VMT energy increased sharply from 60.58% to 81.14%. This may indicate that although the absolute TSI level became lower, the month-to-month change became steeper. In other words, the slope of the TSI curve changed more abruptly during this period, which increased the accumulated energy despite the lower overall TSI values. From a VMT viewpoint, this pivoting point may represent a temporary internal restructuring process of the post-stroke biomed ecosystem rather than simple deterioration or improvement alone. Nevertheless, my post-stroke TSI values remain below 100, which is a relatively safe zone. Personal reflection: after my stroke, my brain gradually became extremely sensitive to small changes in glucose and blood pressure. Sometimes I can almost feel the trajectory behavior internally before looking at the actual numbers. Over the past 11 months, the TSI-Stroke model slowly transformed from a mathematical equation into an intuitive warning system inside my brain in the form of a movie. I now perform repeated blood pressure measurements many times per day because blood pressure behaves like a high-frequency dynamic system. Repetitive measurements allow me to observe transient spikes, oscillations, and trajectory shifts that traditional occasional office measurements completely miss. I have never been labeled as a chronic hypertension patient, however. One acute hypertensive spike of 175 mmHg almost killed me. That is why I measure my blood pressure so diligently, in order to capture this sudden and silent killer. At the same time, I have also closely monitored my glucose and pulse pressure to make sure they are not building a physiological platform high enough to amplify an acute SBP spike strong enough to kill me. In contrast, glucose remains relatively stable overall, usually below approximately 110 mg/dl. However, even small increases after my stroke appear to amplify the sensitivity of the overall TSI-Stroke system. Through continuous observation, I gradually realized that the human brain itself may function as a powerful adaptive pattern recognition system after repeated exposure to high-frequency biomedical feedback signals. Using an appropriate metaphor, a slowly rising structural platform eventually became high enough for an acute SBP hammer to strike my brain and trigger a stroke. This was how I felt. Conclusion: the study demonstrates that statistical correlation and VMT energy analysis describe different aspects of the same biomedical system. Statistical correlation primarily reflects geometric synchronization behavior within the time domain. VMT energy analysis reflects accumulated physiological stress and nonlinear triggering force. Although SBP showed only approximately 11% statistical correlation with TSI-Stroke, however, its VMT energy contribution remained nearly equal to glucose and PP. This finding strongly supports the structural validity of the TSI-Stroke multiplicative equation. The study also demonstrates that multiplication may better represent nonlinear biomedical interaction systems than traditional additive approaches because multiplication captures amplification behavior among coupled physiological variables. From my viewpoint, stroke triggering is not caused by one isolated biomarker alone. Instead, it emerges from nonlinear interaction among chronic metabolic stress, vascular stiffness, and acute mechanical pressure force. The combination of VPT geometry analysis and VMT energy analysis may provide a deeper understanding of dynamic biomedical system behavior beyond traditional statistical interpretation alone. Epilogue: after my hemorrhagic stroke, I no longer view blood pressure and glucose as isolated laboratory numbers. I now see them as dynamic interacting forces continuously moving inside a nonlinear biomedical system. Over time, my research gradually shifted away from purely mathematical modeling toward real-time survival monitoring and physiological pattern recognition. The TSI-Stroke equation eventually became more than an equation. It became a continuous survival warning language and images between my brain and my body. Perhaps this is one of the deep meanings behind long-term longitudinal self-observation. Mathematics slowly becomes intuition, and the intuition slowly becomes survival awareness. Disclaimer: write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to T.E. author, Gerald C. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.